Today we are going to study some properties of Dirac delta function. So let me write properties of Dirac delta function, delta x. Okay. Before that, last time we learned that Dirac delta function is a function such that for all values of x not equal to 0, I repeat, Dirac delta function is a function such that this is equal to 0 when x is not equal to 0, and this is equal to infinity when x is equal to 0. And then we also had integral from minus infinity to plus infinity delta x dx. This is equal to 1. Okay. And then we also had another property that is from integral from fx, integral fx delta x dx, where we take the limit from a to b, and a to b encloses the origin. Okay, a to b, the limit a to b contains the origin. If fx is a well-behaved function, then we have this is equal to f of 0. This we discussed last time. Okay, so today let us study some properties of the Dirac delta function. So the first property, let me write it down here. First property that we are going to study is that Dirac delta function is an even function. I repeat, Dirac's delta function, this Dirac's delta function is an even function. What does it mean? Even function in x. Even function in x. What does it mean? It means that delta of minus x is equal to delta of x. Okay, this is what we mean by even function. Okay, this is fine. Okay. Property number 2. Property number 2 is this Dirac delta function of a times x, where a is a constant. So a times x, this is equal to 1 by modulus of a delta x. I repeat, Dirac delta function of a times x. This is equal to 1 by a, the Dirac delta function. Okay, and how are we going to prove this? Okay, we can prove this by starting with the, to prove this, let us start with the integral fx delta ax dx from minus infinity to plus infinity. Okay, let us call it I. Let us call this integral I. Now let us consider the case where a is greater than 0 first. So if a is greater than 0, then let this ax equal to y. Let ax equal to y. Okay, then this implies x equal to y by a, and dx is equal to dy by a. Okay. So in this integral, if we substitute ax equal to y, and then we express the integral in terms of y, what should we get? We should get this integral I is equal to integral f of x. And what is x equal to? X is equal to y by a. So this is f of y by a. Okay. Times delta of y. And what is dx equal to? Dx is equal to dy by a. Dy by a. Okay. And what are the limits? Here, when x is equal to minus infinity, and since a is positive number, when x is equal to minus infinity, y should also be equal to minus infinity. And when x is equal to plus infinity, y should also be equal to plus infinity. Okay. So this is f of y by a, delta y dy by a. Now I can take this a is a constant, so I can take 1 by a outside. This is integral from minus infinity to plus infinity, f of y by a delta y dy. Okay, now we get this expression. And let us look at this expression here. Integral from a to b, f of x delta x dx. Here, if a and b contains the origin, then this is equal to f of 0. So instead of x, we replace 0. So we use this property. Sige property se koi seasonality. So here we have f of y by a delta y dy, and from minus infinity to plus infinity, and it contains the origin. Okay, so this is equal to 1 by a, this 1 by a times f of, now you put y equal to 0 here, 0 by a. And 0 by a is nothing but 1 by a f of 0. Okay. Fine. So what have we obtained here? We have obtained that this integral f of x delta ax dx, this is equal to 1 by a f of 0. Okay. So this is nothing but, this is equal to integral from minus infinity to plus infinity f of x 1 by a delta x dx. Okay. This 1 by a, I can bring it inside, and f of 0, this this f of x delta x dx, this is equal to f of 0. So I can write this as integration from minus infinity to plus infinity f of x 1 by a delta x dx. So this is equal to I. So when we compare this and this, I repeat, when we compare this expression and this expression, what do we get? We get that delta ax is equal to 1 by a delta x. This is for positive a. Now for negative a. Okay, well, first let me write, therefore delta ax is equal to 1 by a delta x. This is for positive a. Now let us try to prove it for negative a. If a is less than 0, if a is less than 0, let ax equal to y. This implies x equal to y by a and dx equal to dy by a. Then the integral I, this is equal to, what is the integral? The integral is this. This is the integral. So let me write it down here. This integral I is integral f of x. X is y by a, f of y by a delta y Now dy by a. Now here a is a negative number. So when x is minus infinity, y will be plus infinity since a is negative. And when x is plus infinity, y will be minus infinity since a is negative. Okay, then this I can take this 1 by a outside, then write the integral, then f of y by a delta y dy. Now I can interchange these limits. When I interchange these limits, minus infinity comes here, plus infinity comes here, and since I have interchanged the limit, I should have a minus 1 factor here, minus 1 factor here. Okay, so this implies 1 minus 1 by a. And what is this equal to? This, as we have seen, this is equal to f of 0. Okay. And what is minus 1 by a? This is nothing but 1 by minus a. And since a is negative, minus a is equal to modulus of a. Okay, f of 0. Right? Okay, and this is equal to 1 by modulus of a integration from minus infinity to plus infinity f of x 1 by modulus of a should be inside 1 by modulus of a delta x dx. F of 0 is 1 by integration f of x delta x dx, and 1 by modulus of a I have taken it inside. Okay, so this implies delta of ax. This implies delta of ax is equal to 1 by modulus of a delta x. Okay, so if I write this as equation number 1, this is for positive a. Positive a is if a is positive, a is equal to modulus of a itself. And this is equation 2. This is for negative a. So combining equations 1 and 2. Combining equations 1 and 2. What do we get? We get delta ax equal to 1 by modulus of a delta x. Okay, this is property number 2 of delta functions. Okay. Now let me take a new sheet of paper. Let me write down property number 3. Okay. Property number 3. This is the shift of origin. Shift of origin. What have we learned? We have learned that integration fx delta x dx is equal to f of 0 when a and b, this interval contains the origin. Okay, this a and b, it can also be replaced by minus infinity to plus infinity. F of x delta x dx, this is equal to f of 0. Because minus infinity to plus infinity, this interval contains the origin. Okay, so a and b can be replaced by minus infinity to plus infinity. And similarly, minus infinity to plus infinity can be replaced by a to b, where a and b, for the interval a to b contains the origin. Okay, so what happens if we change x to x minus x0? That is when we shift the origin towards the right by an amount x0. So let me show it here. Shift of origin. There is integration from minus infinity to plus infinity delta x minus x0 multiplied by f of x dx. If there were no x0, x0 is around this is simply f of 0. But so x minus x0 higher, if here we have delta x minus x0, f of x dx, then this should be f of x0. Okay, x0. We have shifted the origin by an amount x0. And this can be proved. This can be proved. This can be proved by making the substitution y equal to x minus x0. This can be proved by making the substitution y equal to x minus x0 and noting that when y is equal to 0, x is equal to x0. Okay, this can be proved by making the substitution y equal to x minus x0 and noting that when y equal to 0, x is equal to x0. Okay, okay, let me try to prove it. So let us take this first. Let I equal to minus infinity to plus infinity delta x minus x0 f of x dx. Okay, this is fine. I repeat, let I equal to delta x minus x0. Okay, this is fine. Okay, then put x minus x0 equal to y, this. Okay, then dx is equal to dy. So in this integration, let us substitute x minus x0 equal to y. So the integral becomes, I becomes integration delta. So x minus x0 is now y. Delta y, what is f of x? This is f of, now x will be y plus x0. So this will be y plus x0. Then dx is equal to dy. And when x is equal to minus infinity, y will also be minus infinity. When x is equal to plus infinity, y will also be plus infinity because x naught is just some finite number. Okay, this is fine. Okay, then this will be equal to delta y f of y plus x naught dy. Okay, now let us look at the expression again. This expression, minus infinity to plus infinity f of x delta x dx f of 0. This is equal to f of 0. That means you simply put x equal to 0 here. So if I put y equal to 0 here, we should get a similar answer. So this would be equal to f of, instead of y, you put 0. 0 plus x naught. This is nothing but f of x naught. Fine. So we have proved this. I is equal to f of x naught. Fine. Okay. This is well and good. Next we have property number 4. Property number 4. Property number 4, it goes like this. If the argument of delta x is a function, g of x with simple zeros, at points, ai on the real axis. Simple zero means the function gx will become 0 when x is equal to ai. But the derivative of the function at the point ai will not be 0. the real axis, and therefore the derivative of gx calculated at the point ai is not equal to 0. All higher derivatives are 0. Okay, I repeat, the argument of delta x, that is the instead of x, if we have a function g of x, and the function is such that it has simple zeros at the point ai. Simple zeros means when x is equal to ai, g will be 0. So ai means there can be more than one simple zeros. So a1, a2, a3, a4, a5, and so on. So ai represents all those simple zeros. Simple zeros means, I repeat, at the value x equal to ai, the function gx becomes 0, but the first derivative of the function at the point ai is not 0. Higher order derivatives are 0. Okay. In such a case, then delta of g of x, this is equal to summation over all i's delta of x minus ai divided by modulus of g prime ai. Okay, this is the fourth property. I repeat, I have a function g of x, and g of x has simple zeros at the points ai. There can be many points. Simple zero means the function is 0 at the point x equal to ai, but the first derivative is not 0 at the point ai. Okay. Okay, that is fine. So let us prove this. Let me take a new sheet of paper to prove this. Okay. Here we have to remember two things. What is the first thing? First thing is this. First thing is this. And the second thing, and what is the second thing? We have to express g of x. We have to express g of x as a Taylor series expansion about the point ai. So we can expand g of x in a Taylor series about the point ai. G of x can be expanded in a Taylor series about the point ai. G of x, this is equal to g of ai plus g prime ai multiplied by x minus ai. And higher order derivatives are 0. And since ai is a 0 of the function g, that means the value of g at x equal to ai, this is equal to 0. So this is equal to 0. So this is gx is nothing but g prime calculated at ai multiplied by x minus ai. Okay, this is Taylor series expansion. Taylor series expansion of gx about x equal to ai. Okay, so this is fine. Next step, we have to take the left hand side of this. So the fx multiply this by fx and then integrate from 0 to infinity. So let us do that. Okay, so let us take the integral from minus infinity to plus infinity f of x delta g of x dx. This integral can be expressed like this. This is f of x delta. This gx, it can be replaced by this. Okay, it can be replaced by this delta g prime ai a1. Let us first start with a1, x minus a1 dx plus integration. This is from a1 minus epsilon to a1 plus epsilon. Okay, and plus let me write a plus here, plus integration fx delta g prime a2 x minus a2 dx, integration from a2 minus epsilon to a2 plus epsilon, and so on for all possible values of a. So far have we done here? We have decomposed the original integration into a sum of integrals, over small intervals containing the zeros of the function gx. And inside each of this interval, we have replaced gx by the leading term in each Taylor series. Okay. So far, so good. Next, what do we do? First, we identify here. First, we identify. Okay. Before doing it, I think we can write it in the summation form. This can be written in the summation form like this. Summation over all values of I, integration ai minus epsilon, ai plus epsilon. Okay. F of x delta g prime of ai x minus ai dx. So this summation, this sum over all simple zeros, it can be written in this shortened form. Okay. Now we should remember that the derivative of the function gx calculated at the point ai, this is a constant. This is a constant. Okay. So this constant, what we learned from property number 1, we learned that, property number 2, we learned that if x is multiplied by a constant, then that constant can be taken outside with a modulus sign. Okay, we use this property first. So we should remember that this g prime ai, this is a constant, so it can be taken outside. So let us take it outside with a modulus sign. So this is summation over I 1 by modulus of g prime ai. Okay, modulus of g prime ai. And what remains is integration ai minus epsilon, ai plus epsilon, delta. Sorry, I have fx here, so let me write fx first. Fx delta x minus ai dx. Okay, this is fine. Delta x minus ai. This is fine. Okay. And this is equal to summation over I. This is nothing but f of ai. So this is nothing but f of ai. F of ai modulus of g prime ai. Okay. This is fine. What have we used here? We have used the shift of origin property. we have used the shift of origin property here. Okay. Now, when you compare this expression with this integral, I repeat, when you compare this expression with this integral, what do you get? We get this final answer. So I repeat, when you compare this expression with this integral, what do you get? We get delta gx, we get delta gx. This is equal to summation over I delta x minus ai, x minus ai, g of g prime ai modulus. Okay, fine. I repeat, when you compare this and this, we should get this expression. So that is the proof of property number 1, 2, 3. That is the proof of property number 4. That is the proof of property number 4. Let us write down property number 5. Let me write it down on a new sheet of paper. Let me write it down on a new sheet of paper. Okay. Property number 5. That is derivative of delta function. Derivative of delta function. That is minus infinity to plus infinity f of x delta prime x minus x naught dx. This is equal to minus integration from minus infinity to plus infinity f prime x delta x minus x naught dx. And this is nothing but minus f prime x0. This is the property. Derivative of delta function z, this is equal to this. So this derivative, it shifts to f prime x with a negative sign. And from the shift of origin property, this is simply equal to minus f prime x0. This can be taken as defining. This can be taken as defining the derivative of delta x. This can be taken as the definition of delta x. It can also be evaluated by performing an integration by parts on any of the sequences which define the delta function. Okay, let me stop the recording here.